Hey, I just realized something. Well, we'll get to it. I might go put the screen up and then put it back down. Is that okay?
Yeah, that's totally fine. It's always pointed to the same place.
Okay.
Right? So that's completely fine. We're going to get started here. So we're happy to have Izaak here. He was a student at UC Berkeley not long ago. And since then, he's been doing some great things in the startup he co-founded called Coda. In particular, there's been a pioneering technology around both zk-SNARKs and proof-of-stake consensus algorithms. So I asked Izaak to come and tell us about it because it is definitely one place where some of the things that you've seen in academic contexts, especially when you do the bootcamp, have not how it should be deployed in real systems. So thank you, Izaak, for coming. Please go ahead.
Thank you for having me. Okay. Hi, everyone. Alessandro introduced me, so I don't have to say too much. Basically, what I'm going to be talking about today is, well, a few aspects of Coda, which is a cryptocurrency system, a blockchain system, that has some interesting properties, and as Alessandro says, utilizes a lot of the technologies which people have learned about so far in this workshop. This is a table of contents slide, as you can read from the title. First, I'll kind of say a little bit goals for the talk, just like things that one should maybe take away, or that I would hope one takes away from this talk, the things that I had in mind while writing it. I'll go over some preliminaries, mostly like some simple crypto definitions. I'll explain this concept of a succinct blockchain. I'll explain the challenges that this setting holds in designing consensus algorithms. And then if time permitting, or if there's interest or whatever, I may talk about these other topics, which is basically dealing with the fact that using SNARKs are pretty heavyweight cryptography, and actually in practice they're pretty slow. So it presents some practical challenges, and then, I spend a lot of my time writing programs that run inside of zero-knowledge proofs, if you know what I mean. Who knows what I mean by that? Okay. So, it's something that people, I don't know, I mean, I guess I've been doing since like 2000, I don't know when Alessandro, but since Matters and Alessandro started doing it in 2013 or something. Either are various metaphors for and ways of thinking about it, so which aren't written down anywhere as far as I know. So I thought it might be nice to just talk a little bit about those, because I think in some ways those are some very valuable artifacts of science and some of the most difficult to serialize in the format of a paper or whatever. So okay. Who knows what I'm saying? Maybe that was confusing. Okay. So, okay, goals. So first I'll kind of talk about what is a succinct blockchain. What do I mean by that? We'll talk about how consensus can possibly work in this setting. Yeah, and I guess these things that I said already. Okay. So, notation, like maybe forget this first bullet point, it doesn't really mean anything. So everything will be in like the setting of cryptography. So all sets, a set is really an ensemble of sets. A function is really an efficiently computable function. Every party is computationally bounded, and everything is up to events of negligible probability. Who has heard of this setting before? Okay. So SNARKs. You said you heard the acronym, but you don't know exactly what it means. Well, usually there's a slide where someone puts like an acrostic, like where it says like S is for this, N is for this, A is for this, blah blah blah. I guess I won't do that. A SNARK is the following cryptographic primitive. Basically, a SNARK construction does the following. If you come up with a function like this from some set, that takes some statement, you call this the set of statements. You call this the set of witnesses. Okay. So if you have a function that is a relation on this set, basically what you can do is let me just, before I hit next on the slide, who already knows what this is, first of all? Just so yeah, okay. So basically it's like this. I know, well, I know how to run some computation to completion. It's a complicated computation. And I want to convince you that I can actually run this computation to completion, but I want to convince you with a very small amount of data, and so that you don't have to spend very long at all thinking about the data. So maybe it can be an arbitrarily complicated computation, but I'm going to send you just maybe some hundreds of bytes, and you're going to spend some maybe milliseconds thinking about it, whereas maybe I took minutes or longer. Okay? So this is the computation. There's some algorithm prove, which takes a statement and a witness and produces an element of this set called a proof. This should be pretty efficient. You have a verification algorithm which takes a statement and a proof and says yes, it's a good proof or not. Completeness basically means for any true statement. So if it's the case that for some statement S, there is a witness value that I can plug in which makes f of S with the witness true, then if I can actually produce a proof and verify should return true on that proof with that statement. Moreover, I shouldn't be able to produce proofs for statements which do not have corresponding witnesses. Okay? So if there is some proof which causes this verification algorithm to return true, then in fact there really ought to be some witness making the original function also return true. Okay? Does that make sense? You who didn't know about SNARKs before.
I didn't know that the notation 2 means binary, probably. True and false.
Oh yeah. 2 means a set with 2 elements, which are customarily called true and false.
It's just a small comment. So I think what the feature is SNARK, it's a G, not a K. Because SNARK means also knowledge.
Oh, you missed the first slide where I said that. Well, I guess I didn't put it on the slide, but for me, exists means really very much exists. In other words, arrow means there is an algorithm which, if you have what's on the left-hand side, really produces what's on the right-hand side.
Yeah.
You need to interpret. I promise there's a way to interpret all the symbols on the slide in such a way that it's really a SNARK. Yes. Yes, that's a good point. So, well, anyway, we don't have to dwell on it. All right. So, okay, yes. So then I said I was going to talk about succinct blockchains. So everyone knows about blockchains, I guess. The usual situation is you have a blockchain. This is you, perhaps. You look at your blockchain. You check the blocks. It looks good to you. But then, some time passes, and the next time you come back, it's quite large. You connect to the network. You want to connect to the network. You want to know, hey, what's the state of things? But now you have all of this data going off and off and off to verify. So what do you do? Well, you go, you verify, and at the end you're quite old and you've wasted your entire life syncing the whatever blockchain it might be that you're interested in. But at least you verified it, so that's good. But actually, there's a better way. Well, all right. So let me first kind of maybe say a little bit more about this. I forgot that I made the slide. Connecting, right? So actually verifying to a blockchain is a real pain in the butt with any blockchain. It takes forever, which in practice creates a lot of friction. It makes it extremely unpleasant. Every time you want to use Zcash, you open your computer, you wait a while for the next blocks to come in. It takes actually a really long time since the last time you used it, and it's annoying. You can forgo verification, which is kind of risky because invalid blocks do get mined. This happened most recently in June on Bitcoin, and so well, yeah. So one alternative is to use so-called light clients and just, for example, check the proof of work or the permissioning. That's reasonable modulo this fact that invalid blocks get mined. Maybe I'll just finish this slide. But right, so if you wanted to use proof of stake, it's not obvious immediately how to actually do this. There's no sort of analogy to just checking the proofs of work. Yeah.
Well, what happened to you, John, with Bitcoin? You were.
From time to time, for whatever reason, I don't know if it's maliciousness or someone forgot to upgrade their software, but from time to time, invalid blocks get mined on Bitcoin.
So some invalid blocks going to Bitcoin in June?
Yes.
And then what happened afterwards?
There was like a pretty long reorg. I don't know how long.
The hard fork. Some kind of.
It got rolled back. Like someone noticed the problem after a while, and they stopped mining on top of it, and then it got rolled back.
So it was showing that many people are not validating the blocks. Like if this invalid block got extended for quite a while.
I think the reason that it happened is because Bitcoin mining is pretty centralized, and it was Bitmain, I think, that mined an invalid block, so they were able to keep it going for a while.
So yes. Bitmain mined on itself, on its own blocks, and or are the people following?
As far as I know, I don't know that much about the incident. It happens from time to time. If you Google Bitcoin invalid block, from time to time there will be an invalid block. Okay, so right. So what is this? Oh, yeah. So what is a succinct blockchain? It's basically like a blockchain where you only store, instead of storing sort of the entire history, you store some summary of that history, which will be small and sufficient to adjudicate between forks. Okay? Like think about Bitcoin, for example. What do you need to know? When you compare two Bitcoin chains, what proof of work chains, what do you need to know? Who can say?
At least the height, at least.
Right, the accumulated number of hashes, expected number of hashes computed on that chain, right? So if you wanted to compare two Bitcoin forks, you just need to look at this one number basically, which says which one has more work in it, right? Moreover, this state is sort of incrementally computable. So if you have the state from time t, and you have a block, you can compute like what ought this state to be in time t plus 1. Namely, you just add what the difficulty was before with the strength of this new block. You see what I'm saying? Okay, so that's what I mean by a succinct blockchain. It's basically a state machine which keeps track of this information which is required to adjudicate between forks. And sorry, let me say one more thing. If you can describe your blockchain, the permissioning mechanism and state of your blockchain in such a way, you can construct a system which is able to produce, instead of proofs of validity of the chain, which are very short and easy to check, which are SNARKs. Okay? So what do you want to prove to the user? You want to prove to them, hey, like this is the state. You know, the set of UTXOs is such and such. The total difficulty is such and such. You want to convince them of that. What's the usual way? You show them the entire blockchain, right? What's the succinct way? You show them a SNARK, which proves the existence of such a blockchain. Does that make sense? Yeah. So that's all that I mean. So this is quite nice for the user because they get a sort of this complete level of security with a much better user experience. This does introduce some constraints for the protocol designer, namely, we need to design our consensus mechanisms in such a way that you can decide between forks using only a very small amount of information, and such that this small amount of information can be sort of incrementally computed. Okay? So, yes. Well, this is a comic explaining the situation. You have here a block producer, perhaps a miner, if you're using proof of work, and every time they update the blockchain, they also create a proof that shows them correctly updating the blockchain. Okay, doing what they were supposed to do. Yeah, so I made a little, just like to kind of drive the point home. Like here's here's one way of thinking about this. You describe your state for Bitcoin. Actually, Bitcoin takes, for the difficulty, it takes an average of the past, right? Something like that. But there's no reason why you couldn't just take the last one. I think Ethereum does that, actually. So all the state that you need to hold on to is, what was the time of the last block? What was the difficulty of the last block? And what was the total weight of the chain as of the last block? And if you want to update this state with a new block, well, you just check the proof of work, right? You check that the SHA-256 or whatever, because I should have said SHA or whatever, of the block matches the difficulty that's prescribed by the state. And then you can update the state in the following way. The weight gets incremented by that difficulty, and you adjust the difficulty based on the time in the block, the time of the last block, and the difficulty in the state. And the last time becomes the time in this current block. Okay, so does it make sense? And so, anyway, so basically, this is kind of what I mean by succinct blockchain. You just need to write down such a state and such a transition function. Oh yeah, so as I already said a couple times, proof of work is really simple from this point of view, right? Like, this is like the whole thing on one slide. It's really very simple. Why can we make this succinct in this way? I guess I forgot to say. Let me just say one thing, okay? I said it, but it bears repeating. You wanna? I don't know who that is. Okay, it bears repeating. If you have a blockchain and you can write down the transition function associated to your blockchain in this way, you can use existing SNARK constructions to sort of build this succinct blockchain thing. Okay? And there's a funny technique. It's really cool. If people want to know about it, I can talk about it, but I probably won't. So why is proof of work so good? Right. So as we know, we can decide between forks with a very small amount of information. We just need to know basically the weight, and that state can be computed incrementally as just like iterating some function, right, with some transition function with some state transitions on some initial state, right? Who's with me?
So I had a question. So the correctness of the block, I mean, you're talking about invalid blocks. That's not part of this definition, part of this being succinctifiable?
Yeah, so it ought to be. So like, this was like a really trivial chain which doesn't have any accounts or anything, and just like accumulates proof of work. But if you imagine that here there's also a commitment to the UTXO set, and inside of here we prove, oh, there is a transaction which has a valid signature, which crosses out some UTXO and creates a new. You see what I'm saying?
Sure.
Yeah. Right. Okay. So so that's proof of work. Now we'll talk about proof of stake. The energy consumption of proof of work, as everyone knows, is morally unjustifiable. So we need to figure out something else we can do. The best that people have come up with so far, I guess, is proof of stake. And I'll describe for you a proof of stake algorithm which works in this context of trying to keep it succinct, which is based on Ouroboros, the Ouroboros family of proof of stake protocols. Yes?
Just to make sure I understand, so when you say succinctifiable, you say it's proof of work such that together with everything you also can generate on the side the succinct proof, the succinct verifiable proof that this string that you have corresponds to our chain, right? To an external guy that it wasn't did this.
Yeah, I guess like to be specific, when I'm talking about succinctifiable, you can think of a blockchain maybe as some kind of state machine, basically, right? Where the state is usually just like the list of all the blocks, and like the update function is just like, oh, check the validity of the new block with respect to the old chain and append it to the chain. So by succinctifiable, I guess I mean another state machine, which has the property that its state is small, and these two, and also the transition function is small, and also these two state machines sort of simulate each other.
I think the question behind is similar to Shimon's concern that a distinguishing between forks is not just about the strength of the chain, it's also about where you build on top of the blockchain. So if you have, for example, accounts, you should maintain set maybe a tree over account services.
Yeah.
You do need the rest of the application to have some.
Yeah. So part of the state will also be whatever data you actually want to keep track of, and part of the transition function will involve actually updating that data and checking that you're updating it properly.
So again, the goal is that if somebody comes in from outer space, they can verify that what they have right now really corresponds to a whole chain that happened before. I don't know what happened, but I know it corresponds to
Exactly. Yeah. Okay, so let me say a few words about Ouroboros Genesis. I'm going to keep it really simple. It's kind of more complicated than this, but you know, whatever. Basically, what you do is you take time, you discretize it into epochs. An epoch is, I don't know, like a day, maybe. And then you take epochs and you discretize them into slots. Okay, slots, think, I don't know, 10, 15 seconds, something like that. I wish I could also, look, I'm sorry for the people watching the video, I'm going to draw something on this board also, just so people have an image. Do we have a marker?
Right there.
No. You have one?
Yeah, thank you for that. Yeah,
Oh, thank you. So it's really going to be a really simple picture. It's just like, you just have to think about it. So these are epochs. Okay, this is time. Epochs are just divided into slots. Okay, and the idea of this family of proof of stake protocols is. Oh, thanks so much. Thank you. So let's say this is now. All right. If you want to know whether you won, like this is now. If you want to know whether you won this slot here, if you should make a block this slot, what you do is the following. You basically run a little lottery with yourself, okay? So somehow you're going to sample a random value. You're going to pick like a random x, okay? And then you're going to check, you're going to pick a random x in 0, 1 or something, and you're going to check, is x like less than like my balance over the total amount of currency? It's not literally this, but bear with me, right? Does that make sense? So like if you have all the currency, for example, then this will be 1, and this condition will always be true, right? So then the question is, okay, well, it can't be a random x, right? Because, I picked a random x, and guess what? It was 0. And 0 is less than, I have 10 or something. 0 is less than 10 over the amount, so I win. Who believes me that I really picked 0?
I don't.
You don't, okay. I didn't. I really did not pick 0. I lied. So, you need some way of kind of being able to run this random lottery in a way that's convincing. And there's a cryptographic primitive for that, which is called a verifiable random function. It kind of sounds like the right thing, right? It's a random function which is verifiable. Okay. So what you do is instead of just sampling x like that, you evaluate your VRF with your secret key. It requires a secret key, but that's fine. And you evaluate on some message. What's the message? It's the current slot number, whatever slot you're trying to win, and some random value, eta. Okay? And the point is going to be, this is how you have to evaluate it, and eta, so you have no freedom in choosing this value, and eta is going to be some value which is random and you couldn't possibly have controlled. Okay? Does that kind of make sense? And the where eta comes from, I'll tell you, it comes from basically looking at the previous epoch, taking all the blocks in there, and hashing them up. Roughly, okay? Roughly. Taking the first 2/3 of it, and hashing them up. Okay? And that's eta. Alright, cool. So, that's pretty much it. So every time you're like, okay, am I going to win this block? You take your eta value from the last epoch, from the first 2/3 of the last epoch, you calculate this random value, and you check it against the threshold, and then that tells you whether or not you won the block. All right, yeah.
So there is a detail, like basically the committee's public key has to be determined before determining this eta, because otherwise there's a selective key attack.
Yeah. Also, the set of keys, the set of balance is also frozen at this point.
Yeah, basically before you elect the eta, you need to fix the committee, the next committee first. And this was actually first suggested in Snow White.
Oh, okay. Yeah, I only know about Ouroboros. Sorry. They happen at the same. They happen at the same time. Is my understanding. Like you fix the set of. You fix the set of. At this point, the ledger becomes frozen. You know that you're going to use for the balances, and also the eta becomes frozen.
If anyone can bias this eta, or then they can do a like selective selecting public key attack. I can choose my public key, so I will get elected. Like I control a bunch of nodes, right?
Right.
These public keys are like I generate my public key
Sure. Yeah.
on my own. So you want to make sure like
you can't try and change your public key after eta becomes fixed. Let me say it like that. Yeah. Okay, so that's basically the idea. Whatever. And then as I said, yeah, that's what I said. Eta was. And then you check your VRF, was it less than this? Actually some little smushing of it, but whatever. And yeah, that's it. Now what's the chain selection rule? Given two forks, so I have two forks, you look at them and you say, hey, how long ago did those forks fork? If they forked fewer than k blocks ago, for some value k, which is a parameter of the protocol, it's like 2000, okay? If they forked fewer than k blocks ago, then you can just pick whichever one is longer. Whichever one has the most blocks in it. If they forked more than k blocks ago, what you do is you basically, it's hard in words to understand it. So they forked a long time ago. What you do is you look at the fork point, and then you look at the S slots, like S time periods after the fork point, and whichever one is longer in that time period, that's the one you pick. So you pick the one that's denser in this early time. Okay? Does that make sense? It's just some rule, right? I mean, it's just something. It's some simple rule.
So like just for today in particular, I mean, you're basically, we will not be worrying about why there are these rules.
No.
We are instead concerned about why these specific rules may or may not make it difficult to achieve this succinctly viable.
Yes, exactly. Thank you for saying it that way. So yeah, are these rules good? I don't know. Ask Vasilis. Are these rules succinctifiable? That will be the question that we'll talk about now. Yeah.
So how would you pick the S, the length of the, because the density might depend on the choice.
Yes, S is S. There's some way to compute what S should be given the definition of this phi function and something about K. It's also I think in the paper. Ouroboros Genesis paper. So are these rules distinctifiable? Well, this one requires checking if something forked fewer than k blocks ago. Is there an obvious way to only keep a finite amount of information about a chain and then know, given these two summaries, if they have a common ancestor within k blocks? Can anyone see a way to do that? Imagine k is considered large. Do you see what I'm saying?
Like just give up and pay linearly in k.
You could do that. Yes, you could totally do that. you would totally just keep a tail of length k, and you do it that way. Okay, but for me k is large, so I think that's not so great. What about this one? So, oh, right. Well, but choosing a longer chain, how about that? Is there a way to do that? Right? You just count, right? You just maintain a counter. How about this one? Looking at the S slots after the fork point and choosing whichever one has more blocks in that period. Well, certainly not. It requires looking some arbitrary unknown distance into the past, right? And then computing something about the whole chain in that region. So that's no good. Right. There's this other thing, which is updating the state required for checking the proofs of stake. Requires performing lookups on a database of accounts, but you can just use a accumulator like a Merkle tree, so that's fine. What's more difficult is this rule about looking at the fork point and making a decision based on that. There's really just no way to do that. So because we can only hold on to some constant size summary, so what are we going to do? Oh yeah.
So if we kind of take a step back and forget for a moment about SNARKs, are we basically trying to ask, is there like a small space algorithm that will kind of go over the chain from beginning to end and declare, it's not like the chain, right? It's also forks at some point, but they go to this ambiguity. Do people try to study this property on itself, on its own, the proof of stake community, or? I mean, it might be good to pitch it to them.
Oh yeah.
You can phrase it independent of the SNARK as a.
Yeah, it has nothing to really to do with SNARKs. Yeah.
Yeah, I mean, I guess I'm also trying to just understand the like the consensus nodes. I guess have to hold on to the at least the state DB or something.
Mm-hmm. Yeah.
And then we are seeing that there are different types of nodes. Like there's consensus nodes. There's maybe lightweight clients like users. There's people who join the system and want to become consensus nodes.
Exactly. Yeah.
So in this case, people who join the system late don't have to like linearly verify the history in the past.
Correct.
They still have to like I guess hold on to the state DB to be able to prove things about the next block.
Yes, that's right. But in particular, users, I mean, don't need to do any of that.
So if I'm a user, I want to like submit a transaction to the system.
Well, submitting a transaction is easy because you can always just, I mean, you don't really need any state for that. But looking up whether a transaction occurred or checking your balance, basically you'll listen to your peers, you'll find out, oh, what's the strongest state? For each state, you get this little proof that sort of stands in for the blockchain that backs it, right? So then you can decide, oh, what's the strongest state? And then you can look up, what's my balance in that state? You would have to query to get a Merkle path or something, an inclusion group. From an untrusted helper.
Okay.
Does that make sense?
Yeah.
Okay. Yeah. So okay. So I'll tell you what we do. So this basically what we did was we just looked at the paper and just tried to redo the analysis and see, is there some kind of constant amount of, it's what you would expect, right? Is there some kind of constant amount of state we can hold on to achieve what they actually need? So this genesis rule of looking k blocks, whether they forked fewer than k blocks ago, that's not really what's needed. What's really needed is checking if these two chains have the same eta value. That's really what they need. And that you can definitely do, right? As soon as you pick the eta, you just hold on to it, right? And that's a small amount of data. Okay? So that's good. Choosing longer chains, still good. And then there's this one, which is somewhat more complicated. And for this, it's pretty simple-minded. I mean, let me not say that. It's not that complicated. And you kind of do what you have to do. You take a min. So let's define like the what does M stand for? The min density or something. Oh yeah.
So same. I thought eta changed every block.
Yeah.
So what do you mean? Like, so are you saving the etas
you hold on to the current ADA.
Oh.
And then if you want to know if two chains, have the same ADA, you just look, just check if they're equal.
You mean the same latest data?
The same latest ADA. You only hold on to the latest ADA and throw away everything else. Okay. And also, let me just point it out, like computing this ADA value is also like incremental because you're trying to like just take the whole hash of basically all the VRF evaluations from the whole chain. So you just hash those in, just keep hashing. Take the old hash it in with the new VRF evaluation.
But isn't that window shifting? You don't have to subtract. Are you losing people out of that window?
Say again?
So is it a sliding window? I mean, I'm just wondering, like that ADA value, updating the ADA value, isn't it?
It's not sliding.
It's not sliding.
It's fixed. It's just the first 2/3.
So every epoch you just compute that.
Yeah.
So I'm assuming, like, I guess, so the blocks contain the transactions, but like there's a timeout window for me to throw away the transactional data. Like you don't want to hold on to the transactional log, right? Is that the goal?
Yeah, exactly.
So, but okay, so there's also some, like, if I somehow get petitioned and I want to join back, like I don't have to essentially get all like I only need to know what's the either on the longest chain at the present to be able to join back.
Yeah, and the associated like database of accounts. So you basically, actually for this you kind of take a sliding window. So you basically take a window which has length 2 times s. I'm not sure how, I can't remember how big s is relative to the size of any info. So like let's say this is length 2 times s, and you bump it, by s.
What's S?
Some parameter, which is related to k. So you compute these sort of overlapping sliding windows of width s, and it turns out actually, if you take them in over all s, that this sort of simulates what's going on here. Okay, and is sufficient. And furthermore, this is totally succinctifiable or whatever because you have to remember sort of like this running sum for 2 windows at a time. You see what I'm saying? But that's it. So
question. When you say simulates, it means that you know how to redo the analysis with this specific quantity, or instead empirically this quantity is similar to whatever.
Yeah, that's what I mean. Basically, if you redo the analysis with this quantity instead of this other rule, it's almost the same analysis.
But basically,
Tighten the analysis,
we
essentially.
believe it is true that it is possible to modify reverse genesis such that it satisfies formally this succinctly viable quantity.
Yes,
So
yeah.
at least one candidate fulfills it.
Yes, yeah, that's right.
It's the same thing for fewer than k blocks ago. Basically says it worked within the last epoch. I mean, because you're assuming the ADA value is the same.
Yeah. So basically, I'm pretty sure the reason that this is the right thing, they don't even really use fork fewer than k blocks ago. They only use that because it implies that they have the same ADA.
Okay.
I think.
I'm just trying to translate from the left side to the right side.
Oh yeah.
So it's basically saying it worked within the last epoch, and then this sliding window thing, you're just showing, I mean, do you show that this like approximates the right thing there?
Yes.
Or,
So yeah, basically the.
or does it, I mean, I guess it's affected by how far away you've gotten from the fork, right? Or
Y-
how big the windows are and stuff like that?
Yeah. So there is some kind of assumption here about like eventually taking the min is bad because like eventually like it just keeps getting lower and lower. So you need to say something about set the parameters so that like the min doesn't get too low too quickly, depending on what that means for you. But yeah, basically this min will be statistically close to the worst lowest density or something in this like this period of size, this window size as. Okay, so that's it. So that's it. It's pretty simple. Everyone sees how this would work in this succinct kind of world, right? So that's it. Oh, I wrote some code, but whatever. Oh yeah, so.
So, but hold on, I'm just
Oh yeah.
So architecturally, is it better to just have like some third-party service provider that compute the SNARK of some checkpoint is part of the chain, and then just like don't modify the current consensus and just like do it on top? And I guess
I don't know. So.
So in fact, in your extension, who is computing those stacks?
Oh, those who are producing the blocks. At least.
The workers, whoever it is.
so how would you?
So that would have to count as part of it also. So how is this stacks aggregated or published, or somebody aggregates them?
Every time you create a new block, you publish the proof corresponding to it as well. At least for the ones relating to consensus. There is another sort of side thing where actually there is some group of totally unrelated people who aggregate them, but I didn't talk about that yet.
And do you have to do this recursive composition? Do you have to verify that the SNARK is part of what you're doing?
Yep.
So
I can also talk about that. So yeah.
Again, like architecturally, why don't we just like don't modify the existing systems and just have like some third parties to compute, like update the 16 proof, and publish it, and people can just like throw away the transactional data if it's not needed, and like you need a mechanism to incentivize people to keep track of the state DB. Like the state DB needs to be sufficiently replicated, but that's kind of like an orthogonal question from the consensus, right? Like I'm saying what I'm unconvinced is why this has to be baked into all this consensus level from a system point of view. Like, is it better to just kind of separate them? It's cleaner, like in some sense, that's cleaner design and maybe easier to like.
I think it's a question of granularity in the sense that if you pick your checkpoints to be far enough, such that the distance between checkpoints dwarfs or is, say, reasonably bigger than this eta or S, maybe not eta specifically, but the S consideration, then relative to the size of the chain, then the small space consideration is less a consideration. So if your checkpoints are far enough, probably it's not so bad. So the question of granularity, how often do you want these checkpoints as a function of the parameters? And because if the checkpoints happen in between these events, it will be that your helpers, not helpers, but these checkpointers, right? These people that produce checkpoints, they will have to work not commensurate to the size of the chain, since the last checkpoint that commensurate to some bigger state. So here you want basically the computation between checkpoints of whatever granularity to basically be proportional to the number of blocks that happen in between, as opposed to some exogenous state you have to put on the side for checking this. So that's my understanding.
Okay, that sounds like a parameter thing, but I'm a little bit unconvinced.
No, but it is a relative thing. If you have a checkpoint, once every few years, and in the meantime these considerations don't come up, then sure, you can consider the computation that happens in 2 years, and probably you don't have to worry about forks in the middle because you see the entire chain, right?
But you don't have to checkpoint that infrequent, or you can checkpoint it every hour or something.
I think that's a choice of what your clients should do. Like if you checkpoint, every few months, you might be cutting out some clients in terms of sync, right? Because
I maybe it's worth mentioning like one design goal was making it possible for a very lightweight client to sync to the current state at any point.
So if you want the self-code to do it, for example, I'm not convinced that before you have the next checkpoint, you have a linear cost, right? Just before the next checkpoint. And if that's a few months, it could be that maybe some
I mean, the third-party service provider can be up to date, right? It can keep computing this proof incrementally.
Before the next checkpoint, as a client, you have to pay linearly since the last checkpoint. And if there
but if the third-party service provider is computing the thing, it doesn't stop. Let's say even it has like a proof for the latest block, and the lightweight client can just ask the service provider to.
It is true that the rules are somewhat orthogonal. You could have the service provider on the side.
But yeah, I guess.
I think the theoretical property is that it would be satisfying. Particularly, the service provider would to make sure that you always have the latest one. It means that you have to have multiple aggregations that are kind of shifted to cover every possible endpoint.
Well, the
Yeah.
service. I mean,
I
the service.
guess if there's new theoretical properties for this approach, I would like to understand it better.
I think they exist.
Right now, I don't understand it.
Probably could be still there.
I mean, I think but what you're saying is there's this computation. There's a computation of the new block, and there's a computation of the new proof. And the block producer, in your world, is still responsible for the computation of the new block, but not for the computation of the new proof.
Yeah.
But yeah, I mean, another person could perform that computation. I don't see why not.
Of course, right? I mean, we could go out and prove checkpoints about Bitcoin today, right? And it would be fine.
Yeah, I mean, usually from like a system rollout point of view, this is like more like an incremental deployment, or like easier to
But that is
roll out and
because
stuff.
if you want a certain level of granularity, you need to design a protocol for that level of granularity, and that's what I think Izaak is doing.
I mean, the third-party proof provider can be fine-grained. They have to use the new proof every
It's too
block.
expensive, right? If you don't design a protocol so that the computation, since this incremental computation from the last proof is commensurate to say just the computation of one block.
But that's like a requirement for the proof, the incremental computation, the proof system.
I agree, but it will affect latency, the throughput and the entire system. If you can't keep up with the system because the proof is too hard to compute, because you didn't make sure that your computation is small enough, then you can't run the system forward.
So
But
that's
certainly-
it's the same challenge here, right? Here also, if the proof is very slow, then that's more like, how do you design really fast?
Well, in principle, even what you say is possible with our system. If instead of the block producer being one person, you imagine it's one person who's talking to a giant computer who is your third-party service provider, and they send them the witness, and then they can create the proof. I mean,
Yeah, I mean, I would
anyway.
imagine like this proof computation is going to be expensive. It's actually easier to like roll it out on the dedicated service provider who may have like special hardware instead of requiring all the consensus nodes to have to be really fast.
Yeah, maybe.
They can outsource the lane if that's right.
Uh-huh.
If they don't want to do it, they will outsource. Just like most miners. Even today, most Bitcoin miners don't actually verify anything, right? They're just a mining pool.
I guess it's just like if you bake it into the consensus layer, it becomes like too complicated for me to think about.
If you don't want, slide.
Something DCL, it's basically mining pool is basically outsourcing the verification costs, even today. Which is like much lower, but it's still, right? Like people mine on a USD token and it's all through a mining pool, so they don't guarantee anything.
Well, I think these are good questions, and I think probably there are interesting trade-offs in this system architecture design space.
Yeah, totally. And there are, you can decouple things even further, right? Like you can make it so consensus nodes don't even have to hold on to the entire state. Like in something that Dan Benet talked about, I saw in some talk of his recently, where consensus nodes just have a commitment, like an accumulator, corresponding to the state, and then someone else provides proofs of inclusion.
It's easier to do for payments, but if it's like a Ethereum smart contracts and stuff, you have this general like the state DP is like a memory of a RAM program.
Yeah, but maybe the third-party service provider, creates a proof that they executed some program properly on the state. Anyway, whatever. You can decouple. All I'm trying to say is you can decouple things even more if that's what you want to do. That's pretty much all I have to talk about. I mean, I have other things that I can talk about. I don't want.
But the key challenge is how to do this recursive proof really fast, right?
Oh yeah, I'm happy to talk about that. There are a lot of challenges associated with that. Should I talk about that, or is cryptography boring to people? Or okay.
Maybe.
Yeah.
Well.
What?
Maybe what the room would first like to hear is what are the actual implications for how quickly blocks can be produced and verified? How does it change the basic performance of the blockchain?
I think the main thing that gets changed is just what the performance is for the end user who wants to sync to the full chain. So there are basically, instead of if anyone ever had the experience of trying to sync a full node of cryptocurrency, I don't know, but let me tell you, it's not very fun. And in particular, it takes many gigabytes and many hours or days. So instead, it takes some hundreds of bytes for the state and the proof, and some milliseconds for verifying the proof.
But yeah, how about on the other end, like how?
How slow is it to produce a proof and so on?
Yeah.
So for this proof that for this proof that consists of updating the consensus state, let me not talk about transactions right now. But for this proof that updates the consensus state and verifies like a bundle of a proof which corresponds to a bundle of transactions, with a GPU and with on my laptop I think that takes like 65 seconds or something like that. With a GPU I think it takes like 10 seconds ish.
For how many transactions?
That's for 0-ish transactions.
Right.
So the transactions. I didn't talk about this at all. There's actually like this other technique of pipelining the proving, which is maybe sort of like this third party who produces the proofs. So like producing these proofs is pretty expensive.
Do you have slides in these? Or?
I didn't have any slides. Oh, sorry. I can put this up now, and then I can be on the video.
About the thumbs.
Should I turn off the...
Unless you can use it.
So even with the GPU, it takes some number of seconds to produce, to certify the existence of a transaction which has a good signature and updates the state in a good way. It doesn't spend more money than it has, and so on. I think it takes, I don't remember the exact number, but it's with these new hash functions and stuff, it's pretty fast now. So it's like, I don't remember, but less than. I don't want to say a number, but I think less than 10 seconds, I think. But that's really bad, right? Because then you'll have like 1/10. If you have to do all this proof sequentially, you'll have like 1/10 of a transaction per second throughput, right? So what you can do instead, and by the way, let me say there's a lot of path dependency in the design of this whole system. Like for your point, there's other ways we could have gone, and yeah. So I don't pretend that every decision made was sort of the cleanest possible one. I think there's lots of arbitrariness. But anyway, so the system actually does the consensus nodes are required to maintain sort of a queue of uncompressed transactions. Okay. 1, 2, 3, 4, 1, 2. How many is this? 1, 8. So you can imagine if you wanted to sort of compress all of these up into one proof, and you sort of recursively verify proofs. This I have pictures for, but we already put the screen up. So what you do is basically the following. You make a proof that says, oh, for example, I saw 2 transactions, right? That got me from some state S1 to some state S2, and this one from some state S2 to some state S3. And then you say, oh, I saw 2 proofs. The endpoints, of the state machine that those 2 proofs talk about match up. And so that's sort of a proof that I can get from some state to S1 to S3. Does that make sense? Do people see what I mean? Yeah. Should I say more about it? Maybe I will, just because I promised I would write things in a bunch of different ways. So let me. this is a drawing representation of what I'm describing, but I'm just saying, like, we want to describe a relation. There exists some number of transactions which get me from a state S1 to a state S2. So if in fact there is a transaction which, you know, when applied to some ledger S1 gives some ledger S2, then we will say that you know, that there is some sequence. This will be the relation that we're defining inductively. That there is some sequence of transactions going from S1 to S2. And moreover, if we have, you know, P a proof of P1 a proof of S1 to S2, and P2 a proof of, this is all I'm saying, S2 to S3, then we have, you know, P3 a proof of S1 to S3. And there's some cryptography that actually lets you make proofs that are succinct and whatever. So does that make sense? So I'm making this tree of proofs. That's what these rules represent. But so at the end of the day, you know, I make some tree, S9 or 8 or something. Yeah, and you know, if I had, let's say I had 8 separate computers, how long does it take me to make this proof? Some amount of time, which is like logarithmic in 9. Well, yeah. Or in 8. So that's all just to say that, like, you can almost completely decouple the throughput of the system from the proving time if you have this kind of buffering. Does that make sense?
There's this new paper on ePrint called Halo, like they have a new recursive proof composition.
Yeah.
Can you comment on it? What's like
Yeah, sure.
Maybe Alessandro also knows the state of the art. How fast can you compute it?
So
It's entirely different discussion. So.
I'm happy to talk. I'm happy to talk about it though. So this is all, you know, currently implemented using this cycles of elliptic curves technique from a paper of Alessandro and others. There's this other technique. The trade-offs are basically as follows. Concretely, at least in the existing implementation, it's much slower. There is sort of a theoretical, or like an asymptotic problem also, which is that verification, at the end of the day, like, you know, you do your chain, right? And at the end, like, you have some proof that sort of stands in for this whole chain. So in the case of Halo, verification of that proof requires performing a multi-exponentiation, which of a size which is proportional to the complexity of like one step of that chain. So you need to do a multi-exponentiation which, you know, has the complexity of, well, I don't know, in practice like a few 100,000 or something like that, which does take some time. So like tens of seconds even. You know, in this setting, verification is like a dozen, 2 dozen milliseconds or something like that, versus like tens of seconds. So like there's a few orders of magnitude separating them. I guess 3 orders of magnitude.
Also, to give you some context for other people, so why are we concerned about the costs of recursion? Well, first, any SNARK, because it has verification is exponentially faster than the computation at test, so it allows for this recursive composition. That is an asymptotic statement. When you actually sit down and you want to build systems that say, okay, I actually literally want to write an NP statement where part of the computation of the NP statement is the verifier's own computation. Now you actually need to unroll the verifier's computation into elementary logical steps, typically it is arithmetic circuits, and now you are deeply concerned about the size of your verifier as an arithmetic circuit. And it turns out, for reasons that maybe are beyond the scope of today, that for concrete constructions of SNARKs today, it is not the case that any snark that is good as a one-shot snark is also good as a recursive snark. This specifically depends on whether you have made an effort to make the verifier compatible with the snark's own language. Okay, that involves additional techniques. So this is the reason for why there is some premium to recursion, because you may make different design choices if what you want to do actually recurs, as opposed to use snarks standalone in one shot.
Yeah. Anyway, I hope it'll be faster. You can do things like, in principle, you could do something like that final verification is really expensive, but maybe you can make a pre-processing snark that certifies one of these halo snarks, right? And the pre-processing snark will itself have constant verification time. So maybe you could do that. Although, concretely, when you think about it, then you'd have to do a multi-instantiation with 200-something bit scalars on 100,000 group, some number of hundreds of thousands of group elements inside of a snark. It starts to look not so good because that's going to be some millions of constraints.
So maybe some people want to, so maybe I have a question for you. So from your perspective, what types of maybe, let's call them deep theoretical questions or serious barriers you have sort of fought with in these particular systems? And I mean it like across the board. Could be recursion is certainly one of them. There's maybe some considerations around succinct-ability of proof-of-stake protocols. Maybe there's also a question around incentives, right? Because there is an entire aspect of incentives. So there are people in the audience who do work in mechanism design.
Yeah. So actually, okay. Let me say something. Let me say something about that because I didn't talk about that at all. There are two big problems with Ouroboros in general when it comes to incentives, and in particular something in our system. So let me talk about Ouroboros in general when it comes to incentives. Well, okay, so there's no analysis that exists of Ouroboros with incentives, with block rewards. Like there is with Bitcoin, right? And here it's even a little weirder because the block, the original analysis is sort of done with a static distribution of stake, and obviously the block rewards change the distribution of stake, and they change it significantly. So if you set up your block rewards in the wrong way, then over time your stake distribution gets really skewed, and whatever assumptions you may have made about the stake distribution probably aren't true anymore. And so yeah, I mean, if you want to know more about that and know more about how I think about that problem or what the right way to set block rewards is, or but I only have heuristic arguments. I don't have any kind of formal arguments. But if you're interested in that, please talk to me. And in particular, there is an unspecified tie-breaking rule in Ouroboros, which has a significant impact. How you set this tie-breaking rule has a significant impact on how the stake distribution evolves over time, depending on your choice of parameters. So that's also totally unanalyzed and important in terms of actually deploying it. And again, I have something which heuristically I think is good, but it would be good to have some more theoretical justification. The other thing, yeah, SNARKs. There's I guess a lot to say about SNARKs. So well, as everyone knows, there's kind of every day, if you want a new SNARK, you can just log on ePrint, go to latest papers, and there will be one waiting for you. So if you want to join the fun, that's a good option. And there's obviously there's people here who can tell you more about that. But I'm trying to think what are the. Oh yeah. So being able to what there isn't right now is I don't know. I mean, so there's something bad about these MNT cycles, which is why they made this Halo system. The bad thing is they're very large. So in terms of the size of the field that you need to use, it has 3 times as many bits as you would otherwise want to use. So they made this Halo system. That's pretty good because it lets you use small fields. It's bad because it has this really high verification cost. The proving time is also really high, but that presumably will be brought down, could be brought down. But I don't really know, it's not obvious, I mean, knowing not that much about it, knowing only how the construction works, it's not obvious to me how you can subvert this fact that it has really high verification time without doing some kind of wrapping thing, but wrapping is really inefficient because you have to do a huge multi-exponentiation inside of a circuit. So anyway, there's still, I guess, an open problem of like do recursion with small fields with no setup or maybe universal setup and have low verification time. That's it.
This is a good point to thank you, and let people into
Yeah.
and then there's time for further questions. So we could have one book for the course. People want to